A galvanometer is essentially a PMMC instrument designed to be sensitive to extremely low current levels. The simplest galvanometer is a very sensitive instrument with the type of center zero scale illustrated in Figure 3-7a. The deflection system is arranged so that the pointer can be deflected to either right or left of zero, depending on the direction of current through the moving coil. The scale may be calibrated in microamperes, or it may simply be a millimeter scale. In the latter case, the instrument current sensitivity, usually stated in A/mm, is used to determine the current level that produces a measured deflection. The torque equation for a galvanometer is exactly as discussed in section 3:1. The deflecting torque is proportional to the number of coil turns, the coil dimensions, and the current flowing in the coil. The most sensitive moving coil galvanometers use taut band suspension, and the controlling torque is generated by the twist in the suspension ribbon. Eddy current damping may be provided, as in other PMMC instruments, by winding the coil on a non-magnetic conducting coil former. Sometimes a non-conducting coil former is unemployed, and the damping currents are generated solely by the moving coil. In this case, the coil is shunted by a damping resistor which controls the level of eddy currents generated by the coil movements. Frequently, a critical damping resistance value is stated, which gives just sufficient damping to allow the pointer to settle down quickly with only a very small short-lived oscillation. Seconds. 3:2 galvanometer 37A, center zero scale. Suspension. Turbine. Soft iron. Mirror. / Permanent. Magnet 0. B. Basic deflection system of a galvanometer. Using a light beam. Figure 3-7a galvanometer is simply an extremely sensitive PMMC instrument with a center zero scale. For maximum sensitivity, the mass of the moving system is minimized by using a pointer that consists of a light beam reflected from a tiny mirror fastened to the coil, with the moving coil weight reduced to the lowest possible minimum for greatest sensitivity. The weight of the pointer can create a problem. This is solved in many instruments by mounting a small mirror on the moving coil instead of a pointer. The mirror reflects a beam of light onto a scale, as illustrated in Figure 3-7b. The light beam behaves as a very long weightless pointer which can be substantially deflected by a very small coil current. This makes light beam galvanometers sensitive to much lower current levels than pointer instruments. Galvanometer voltage sensitivity is often expressed for a given value of critical damping resistance. This is usually stated in microvolts per millimeter. A megohm sensitivity is sometimes specified for galvanometers, and this is the value of resistance that must be connected in series with the instrument to restrict the deflection to one scale division when a potential difference of V is applied across its terminals. Pointer galvanometers have current sensitivities ranging from 0.1 to 1 WA/mm. For light beam instruments, typical current sensitivities are 0.01 to 0.1 Pa per scale division. 38 Electromechanical instruments Chap. 3 Figure 3-8 An adjustable shunt resistor is employed to protect the coil of a galvanometer from destructively excessive current levels. The shunt resistance is initially set to shunt S0, and then gradually increased to divert resistance current through the galvanometer. Example 3-2. A galvanometer has a current sensitivity of 1 A/mm and a critical damping resistance of 1 K registered to. Calculate A. The voltage sensitivity and B. The megohm sensitivity. Solution. Voltage sensitivity equals 1 K0 Q.x1 WA/mm equals 1 mV/mm. For a voltage sensitivity of Vim, megohm sensitivity equals 1 B. 3 to 3 DC. Galvanometers are often employed to detect zero current or voltage in a circuit, rather than to measure the actual level of current or voltage. In this situation, the instrument is referred to as a null meter OT null detector. A galvanometer used as a null meter must be protected from the excessive current flow that might occur when the voltage across the instrument terminals is not close to zero. Protection is provided by an adjustable resistance connected in shunt with the instrument. See figure 3-8. When the shunt resistance is zero, all of the circuit current flows through the shunt. As the shunt resistance is increased above zero, an increasing amount of current flows through the galvanometer. Galvanometer applications have been largely taken over by electronic instruments that can measure extremely low levels of voltage and current. These instruments are discussed in section 15-4.